All right. Well, hello everyone. Welcome back to the Beaver Science Speakers Series. That is a mouthful every time. So I'm really excited today. We have Katie Larkin speaking. Um, yep, there she is. And she's looking at stream bed functionality, and you'll look at the effects of beavers, but there's many other things, so hopefully we can branch out as well. So let's see. Katie is from Lancaster, Pennsylvania originally, but got into geomorph, on trips to the West and around the world. And I think, like a lot of us geomorph folks, it was looking around at landscapes and saying, "Why is that like that?" Yeah, I think that's awesome. So you did her undergrad at Washington and Lee, where she got into fluvial geomorphology and some research. She was an environmental consultant working on some soil and groundwater remediation, and then got back into the research game by doing a master's at Colorado State University with Ellen Wool. And she is now continuing on to do a PhD. Are you just starting it now?
I'm actually just I transitioned with no time off in between my master's and my PhD. So
Yeah.
this upcoming semester that starts in less than 2 weeks is taking 4 classes to start my PhD. So really exciting.
Yeah, sorry, I interrupted my own intro. Um, she focuses on using kind of field-based investigations as well as remote sensing to characterize streams and their functions and uh, essentially. She's right now for a PhD, and you can correct me if I'm wrong on this, but focusing on how kind of drivers of geomorphic change, sediment, vegetation, hydrology correlate with the response we see in streams and I would imagine riverscapes in terms of sinuosity, patches, vegetation, I'm sure bed form. And so this is, overall helps give us, an understanding of how streams function and respond, but also, definitely has applications for process-based restoration, as well as just kind of assessing stream and riverscape health. So with that, I will hand it
Right.
over.
Sweet. So if someone could just let me know if y'all can see my screen.
Yes, it looks great.
Perfect. Okay, thank you so much. Thank you for that lovely introduction. I really appreciate it. As was said, my name is Katie Larkin. I am a fluvial geomorphologist doing my PhD and having just finished up my MS under Ellen Wool at Colorado State University. And so my research primarily for my master's thesis focuses on flux attenuation in mountain headwater streams. But today I'm going to kind of like focus in on a little piece of that, which is specifically the influence of beavers on flux attenuation in mountain headwater streams. So I understand that the title of my research kind of throws a couple terms that people might not be familiar with, depending on your background. So I first want to start off with a little bit of a metaphor to kind of explain and set the scene for what I'm going to be talking about today. So I'm sure a lot of you are familiar with the 9 to 5 grind where you finish up work and you try to get on the highway back home, and your commuting on-ramp might look at something like the image on the left, crowded. And then as a result, your highway commute home is quite congested and looks a little bit more like the image on the right. However, our highway and traffic managers and researchers have figured out that putting a simple stoplight on an on-ramp can actually reduce congestion dramatically and make your highway commute home look a little bit more like the image on the bottom right. So while it seems counterintuitive, sometimes slowing down is good. In the context of rivers, we often think of them as facilitating the downstream from headwaters to mouth transport of sediment, water, nutrients, particulate matter, things like that. But in reality, we need that balance of slowing down and speeding up in order to maintain a healthy ecosystem and healthy functions. So if we think about those two conditions as end members, a river that's all go is going to look something like what happened in Hurricane Helene. It's destructive, it's erosive, and it's really just kind of ripping everything out in its path. Whereas a river that is all stop is going to be stagnant and maybe a little bit disconnected. So we need that balance. Luckily, up in the mountains where I do my research, it's actually quite easy to see where these areas of slowing down and speeding up are because they have two very, very distinct morphologies. So on the left here, this large green patch is what we call a bead. And on the right here, this area is called a string. So you can kind of see what they look like in terms of their physical differences, but They also have distinct functions as well. So our beads are laterally extensive. They have large floodplains. You can see that there's a lot of meandering of the river going on in there. They also typically have a lower gradient. And as a result, water flows a little bit slower and there's a lot of storage going on in these beads. So they're disproportionately important to our river ecosystems and also host a lot of biodiversity. In contrast, our strings, laterally confined, you can see there's really not much of a floodplain going on there. They're a lot steeper, so water is just flowing a lot faster, and it's a mostly transport-dominated regime. So I really like the analogy of beads and strings, because if you look at them in plan form, especially in a row of several of them, it looks like beads on a necklace, which is really fun. Some people in my local research area also call them Poudre pearls, because the Cache la Poudre River is an area we do a lot of research on. So I think that's awesome. We can also think of beads and strings as having two different kinds of connectivity that essentially kind of summarize their functions. So our beads are dominated by lateral connectivity. That is essentially the ability of the water in the channel to make it out onto the floodplain. When we have that ability, things are able to slow down and be stored more readily. And in contrast, our strings are dominated by longitudinal connectivity. That is how fast stuff gets from point A to point B. So with that in mind, I wanted to define the other term that I described, functionality. So in the context of my research, I defined functionality as bead ability to attenuate fluxes or absorb and distribute incoming energy. So how good is it at forcing things to slow down? So that term can seem a little bit airy and in context to try to measure directly. So what I did is I picked several, 4 in particular, proxy variables that I believe summarize functions that go on in what we believe to be a bead that is just that is functional. So we know that fluxes in functional beads tend to travel slower, so things slow down and are stored more readily. So in terms of slower travel time, we know that a high total sinuosity, which is how bendy the river is, how much meandering is going on, and also this includes secondary channel activity. So high total sinuosity typically means that things are slowing down. We also look at patchiness, which is essentially this diversity of floodplain topography, biology, geomorphology that contributes to different roughness values. So if water is hitting a floodplain that is all one type of vegetation or one elevation, it's going to have a much easier time getting around than a flux that is hitting a floodplain that is very topographically diverse and has a lot of different kinds of vegetation. So in terms of storage, I use 2 different remotely sensed measures, normalized difference water index and normalized difference vegetation index. And these 2 examine respectively the amount of ponded and like surface water storage, as well as soil moisture. And NDVI looks at vegetation stress. So both of these are indicators that there's plenty of water in the surface and subsurface, and are indicators that everything is connected and is being stored. So now that we have a definition for what functionality is and what I typically look for, I like to think of it as being a system that is driven by system inputs. So these are what I call my drivers. So I was able to separate these drivers out into biology and geomorphology, and separate geomorphology into water and sediment. So today I'm going to only really be specifically looking at the Beaver aspect, because I am giving a talk for the Beaver Institute. But as a very interdisciplinary scientist, I am going to mention, and then I will not mention them again, but I will mention the other factors that I study, because it's not only Beaver that are playing into it. We have to consider the fact that there are lots of different system inputs that are influencing functionality. So my geomorphic drivers, I look at proxies for water and sediment because they're very difficult to measure directly. Specifically, I look at catchment geometry, specifically the relationship between size and amount of water that's coming into the catchment or coming into the river from the catchment. And I also look at elevation for there's a threshold that determines the river's hydrograph, whether it's dominated by snowmelt or whether it's dominated by snowmelt and convective summer storms. And for catchment or for sediment inputs, I look at catchment burn and slope, assuming that there's a lot of wildfires out here in Colorado. And when we have an idea of how severely burnt and how steep our catchments are, we have a better idea of how much sediment might be inputting into the system, assuming that systems with high severity burn and steeper catchments are going to be contributing more sediment. So those are my geomorphic drivers. My biotic drivers that are not beaver, I look at large wood and I look at riparian vegetation, knowing that both of those contribute, large wood in particular, both pieces and jams, those can facilitate deposition and scour, alter hydraulics in the channel and also on the floodplain. And riparian vegetation in the channel and floodplain has a very similar effect. And the moment you guys have all been waiting for, beaver modifications are another thing that I study in the context of functionality. So specifically, we know that beaver modifications enhance floodplain channel connectivity. They increase geomorphic diversity and other kinds of diversity. They slow down and store water. And they create fire-resistant riparian buffers. I believe Emily Fairfax was in here talking to you guys a few weeks ago, maybe. So you guys are probably very familiar with what she's figured out. And we also know that these modifications are quite persistent even after beaver occupancy ceases. So essentially, I believe that beaver are a very, very important part of functionality and have a lasting effect on flux attenuation in rivers. So to summarize what my research exactly does on a more broad context, I'm kind of trying to figure out this overlap here between measuring the magnitudes of fluxes themselves, so what the system is receiving, and then also how to characterize the physical impacts of those inputs. So how biology and geomorphology drive functionality in river corridors. But for today, since I said I'm narrowing down a little bit, I want to specifically kind of narrow in on what we can learn from beavers, both as scientists and as practitioners. So what are we seeing out in the field? What was I measuring? And how can we use that to define our management strategies and our restoration strategies? And also, how can we characterize the spatial and temporal extent of their influence? So now that I've kind of set the stage a little bit for what exactly I do, I want to detail where I did my work. So I picked 3 primary catchments in the Front Range of Colorado, and I picked some different beads in the Cashlaputo River and the Big Thompson River and the St. Vrain River. I also had one little straggler of a bead that was outside across the Continental Divide, Phantom Creek, but for a total of 52 beads in 27 subcatchments. So some of these beads were on the same catchments, but all of them were distinct units of their own. I also, when I did my field work, I noted that there were different, that most beads looked actually quite different. There really was no one template for what they all looked like. They had different sizes, different appearances, but I was able to kind of shelve them into 3 different broader categories. And so I wanted to explain what those categories were, and because they're going to come back in handy later. So I saw that there were beaver meadows, there were elk grasslands, and there were forested beads. So today I'm mostly going to be focusing on these 2, our beaver meadows and our elk grasslands, because forested beads did not really tend to have as much beaver activity. They're very interesting, and I will be publishing a paper at some point in the upcoming months about my findings. So I'm so sorry, excuse me. So please feel free to come back if you want to learn more about those. But in particular, our beaver meadows are these areas that I saw that had a lot of beaver activity, multi-thread channels, lots of soil moisture, lots of willow. They're very complex, and they had that wildfire resistant buffer effect like I talked about. My elk grasslands that I saw were these single thread systems, a lot drier, a lot grassier. Some of them had exposures, as you can see up in the image of the Big Thompson River up in the top right. But generally, they were a lot less complex, and some of them were, their wildfire risk is quite varied. So when I was out in the field, I also, I wanted to characterize how exactly I measure these beads and what I'm looking for. So in the field, I measured my channel width and depth and substrate. And then I found minimum, median, and maximum floodplain width. And from there, I was able to get the ratio of floodplain to channel width. This is kind of giving us an idea of the available amount of floodplain that can be utilized by the channel. How much room is there for the river to expand? So when we have a higher ratio, there's more room for the river to expand outwards and vice versa. I also got the inlets and outlet points. essentially where the bead starts and ends, those elevations, and the length between them to get my bead slope. I was also able to, using ArcGIS, I was able to get areas for these beads, which was quite important. And then also I characterized beaver berms and beaver activity. In particular, sometimes you can see those on satellite. So I've highlighted 5 really nice ones here up at Fall Creek. But in the image on the right, you can see that they also can be quite distinct when you see them out in the field. So I was able to characterize those as a minimum count of the number of berms, assuming that I'm human and I might make mistakes and miss a few, especially if they're quite, some of them tend to be quite degraded and can be really, really difficult to see in person. So that was a minimum count and not an absolute count. And I also looked at the density of these berms. So how many of them per unit length of the bead. So for these variable, and I'm sorry, I meant to say, I measured a lot of other other variables that pertain to my other variables like large wood, water, sediment, but I have decided not to talk about those, just to focus on beaver today. As for my functionality variables, I used remote sensing to calculate my NDVI and NDWI. Specifically, I got min, max, average, and range. Today, I'm going to be focusing on the range for reasons I will explain a bit later. For patch metrics, I used a combination of field and remote. In the field, I was able to characterize these differences in patches and process domains, essentially. So areas that have different functions, both geomorphically and biotically. So for example, here, this is in Glacier Creek in Rocky Mountain National Park. You can see that there's a pond. It's a lot lower in elevation, different, more marshy veg. Up in the middle of the image, there's a beaver berm, which has a little bit denser and greener vegetation. And in the uplands and the further on meadow, there's some willow and conifer. So from those, I was able to calculate or to create these different maps for each bead, which were kind of roughly mapped out of the different patches based on what I saw in the field and what I was able to detect in remote. So these, I'll give you a second to kind of look at the different kinds of patches, but all of these have different functions. And I also was able to include human influences. So up in towards the top of this bead, you can see that there's a road that's running through that I was able to map. And from there, I got a count of the number of patches and the density of patches per area of the bead. And for total sinuosity, I just used Google Earth Pro to calculate the ratio of channel length to valley length. So as a field scientist, I find, and also a visual learner, I find it is really, really, really important to do a lot of documentation in the field. And also I wanted to share some of the images that I saw with you, just so you guys get a better idea of just how impactful our beavers are and how distinct our beaver meadows were in the context of beads in the Front Range of Colorado. So I noticed a lot of differences, and I'm going to characterize these differences for you with some photos. So in particular, this image right here, all of these have to do with different kinds of sediment that result from beaver activity. So the image on the left is beaver fill. It's this really, really dense, moisture retaining, organic rich material that is often made up of berms. It's very erosionally resistant and can alter river morphology. This image in the middle is beaver sedimentation that fills up these ponds that are created. Also, you can see that sometimes there's incision that goes that occurs after these ponds drain. And in this other image, there's these kind of cyclical deposits that result from probably, I'm not super sure what they're resulting from, but likely some sort of cyclical like infilling and draining, or maybe different flood events. I'm not sure, but either way, there's beaver activity that's influencing sediment. We also saw that bank structure and stability are different in beaver meadows. So these two images are showing how berms are retained in the banks and also sometimes across the channel. This one in the top is actually a bridge. The channel is kind of flowing underneath it. You can't really see it super easily though. And this one on the bottom is just a bunch of sticks that have kind of been retained in the bank and are causing it to jut out a little further. So looking at these, in contrast, in beaver meadows that have begun to degrade and have been inactive for a while, I saw a lot of bank instability. So slumps, tension cracks, full-on collapses, things like that. So that was a good indicator of general age of beaver activity and also stability. I also noticed differences in vegetation. So specifically, these really connected, very wet beads, you could often see where the outline of the bead was based on the vegetation difference. So this one on the left is from Elkhorn in Colorado. This one on the right is from a bead in Pennsylvania, where I'm from. I've started to kind of expand my study areas a little bit for my PhD. So I had to include that photo because it's too good not to share. I also noticed that willow and beaver have a very strong, mutually beneficial relationship. And a lot of these berms, even if they were breached or just simply hadn't been ponded in a while, they still have these large willow colonies that often indicate where they are. There's also different elements of floodplain roughness that beaver contribute to. So specifically beaver canals like this one at Fall Creek, these can be activated at high flow, can influence secondary channel activity. They're also a huge tripping hazard if you have weak ankles like me. We also saw that beaver tend to cut things down. So a lot of these stumps and fallen logs on the floodplain contribute to patch density as floodplain roughness elements. And lastly, we saw that this is Ellen for scale in this photo. She's not a particularly short woman, but this berm is as tall, if not a little taller than she is. So these berms can be really, really, really large and can do quite a number in terms of floodplain roughness and flux attenuation. We also saw channel and floodplain hydrology was different. So in particular, this is a pond that's actually located off the main channel. You can't even see this channel in the background, but this water has just been retained here for a while, and Google Earth imagery has shown it's been ponded like that for a while. We also, as beavers are most famous for doing, know that they tend to dam. They tend to build these dams, both on the main channel, such as these two at Pennant Creek, and also on side channels and on the banks, such as these two examples from North St. Vrain and Mill Creek. And lastly, for my last slide about all these field impacts, we know that beavers have a really distinct influence on channel morphology. So even in systems that are degraded, we still see that the channel often kind of forms around these berms since they're so erosionally resistant. So in particular, this berm right here, you can see it kind of jutting out, has created this really interesting, almost like I believe it's an omega. Yeah, it's an omega kind of shaped, almost two 90-degree angles, river bends. So that's really interesting. And this example at Swamp Creek, we zoom in a little further, we can see this really nice little straight segment right here. Oftentimes the erosional resistance of this berm, of these berms, can cause not only these omega shaped segments, but straight segments as the river runs down and finds the area of least resistance to cut through. So with all of this field stuff being said, I wanted to provide some numerical evidence to support my belief that beaver activity is super, super, super important to flux attenuation. So what I did, just kind of in shorthand, and I'm happy to take more questions about my statistical analysis, but I don't want to talk for too long about it. So I'm just going to kind of give a basic rundown of what I did. I did a categorical assessment. So essentially I looked at the one-to-one relationships between my drivers and my responses. So essentially asking questions such as, how does patch density vary by vegetation type? And I was able to use those to kind of influence some of the further testing I did, and also just look at these relationships as they exist. But knowing that most issues in geomorphology and in science in general are not one-to-one relationships, I also did a model selection process. So essentially using my functionality variables, my sinuosity, NDVI, and NDWI, and patch density as my outcomes, I inputted all of my different variables, both biotic and geomorphic, and I let the selection process do what it did to find the driver variables that had the best chance of explaining variation in my functionality variables. So with that, I was able to get these finalized models. So I wanted to give you guys the finalized models right here. Oops, what the heck? So for total sinuosity and patchiness, NDWI and NDVI. So if we're looking at these a little bit, we notice that the most commonly appearing variable is bead ratio, which is essentially the ratio of catchment size to bead size. So how big is that catchment in relation to the bead? So that can influence a lot of different things. It can influence the hydrograph, it can influence sediment, it can influence burn. So it's pretty clear that that ratio encompasses a lot of the different inputs. Interestingly, also, we see that the only variable that has beaver activity in it is patchiness, specifically berm density and minimum berm count. And even more interestingly, I noticed that a higher berm density was associated with higher patchiness. So more closely spaced berms was associated with more patchiness, and that a lower minimum berm count was associated with higher patchiness, which I believe I can attribute to the typically larger size of outgrasslands. Those had a lot more berms in them typically, but they weren't quite as patchy. So looking at all these, I wanted to kind of dive a little bit deeper into where beaver fit into this relationship. But most specifically from this, I was kind of able to rule out beaver as having an influence in sinuosity, interestingly. I'll go into that more a little bit later. So when I decided to dive a little bit deeper, I figured out that looking at patchiness and NDVI and NDWI together was actually a really interesting thing. So I have pulled up on the screen right here these two examples, really good ones of a beaver meadow and an elk grassland. So our beaver meadow up at the top here, you can see the different kinds of patches I've illustrated. Typically a lot more universally wet. So our wetlands, our channel, our ponding, our berms all tend to store a lot more water. So it's patchy and it's wet. And in contrast, our elk grasslands down here, while there's still a lot of patchiness, there's a big difference in the hydrology. So for example, our grassland areas and our highlands tend to be a lot drier, whereas our river channel, our berms, and our relic channels tend to store a lot more moisture. So even though these two were both quite patchy, there was a very clear difference in what those patches entailed for hydrology and connectivity. So when I looked at it a little further, I found that beaver meadows, this patchiness was indicative of geomorphic heterogeneity. The highest patch densities were found here. And our elk grasslands, even though they were quite patchy, were more indicative of this hydrologic disconnectivity. So with that, we had our highest NDWI ranges and NDVI ranges. So these high ranges, we would expect a range that is higher to be indicative of more diversity of conditions, especially using a term like heterogeneity. That seems like it would be a good thing. But in this case, that means there are some areas that are really dry and some areas that are really wet. So this doesn't necessarily indicate functionality. If anything, that tells me that there's a lack of functionality, that it is not universally wet across the floodplain. So with that being said, I was able to kind of determine that elk grasslands and beaver meadows are statistically distinct process domains. They are two areas with different geometries, functions, geomorphologies, and biologies, among other things. So I also kind of described this as, hold on, pardon me, my computer is about to die. I should have put it on the charger. I'm gonna pop it on there really quick. Don't mind me. Thank you for bearing with me, everybody. I appreciate it. Okay, back to the scheduled programming. So I've kind of named beaver meadows and elk grasslands as this kind of system of end members where we should be considering it more as like a continuum of conditions. So in the case of our active beaver meadows, we would consider these areas to be to have present, accessible, and active beaver modification. And our elk grasslands would have signatures of beaver activity, but they're not active, they're not accessible, and they're only minimally present. So in between these two, I believe it is a little bit wiser to propose two different other kinds of conditions. So specifically the inactive intact meadow, where there are present and accessible beaver modifications, but they're not presently active. So the system is starting to degrade, but is not not super far in its degradation process. And the inactive incised meadow, where there are beaver modifications present, but the system has started to degrade and incise down to a point where they are not accessible anymore. So looking at the system, it's still a little bit choppy to break it into four, but I hope this kind of signals a little bit that the transition and the degradation of beaver meadows into elk grasslands is a lengthy process, and it is one that is able to be detected in the field and remotely by practitioners and scientists. So I'm proposing that it is a wise idea to examine the state of our study sites in order to determine whether they are good fits for restoration and other things. So specifically, I think it's wise to adopt a field and remote strategy. Those two work really well together by providing us physical evidence in the field of indicators of connectivity or disconnectivity. And also the remote aspect provides us information about stuff that is harder to detect in the field, such as larger dynamics of patches and also just floodplain hydrology. So in the field, what we might look for, conifer encroachment. So our conifers are indicators of drier patches. They prefer higher areas and they prefer drier soils. So if we see a lot of conifers making their way into the floodplain, that'll typically be an indicator that conditions are starting to dry out a little bit. This is a problem that is pretty widespread across Colorado, and I saw quite a bit of it. We can also look for bank instabilities. So these bank instabilities, as I showed earlier, I found in the degrading beaver meadows, typically the ones that had started to incise and had started to kind of approach that critical bank height in which the bank is past a threshold of stability and will start to actively fall in and degrade. So these can look like tension cracks. These can look like slumps. They can also look like these large cohesive chunks of bank material that kind of act as clasts in the riverbed. Super interesting. Quite fascinated by those. We can also look for secondary channel activation or conversely abandonment. High flow marks can be an indicator of how far up the river is able to access, whether it's able to access the floodplain or not. And lastly, indicators of beaver activity, and specifically how old those indicators are, might give us an idea for if they're still active on site, and if they're no longer active, how long have they been inactive for? So how long has the system been actively degrading for? Things that we can test for that are not necessarily in the field. So going back to my model of sinuosity, there are some variables that play into functionality, such as elevation, confinement. So confinement has to do with outcroppings of bedrock, essentially immovable boundaries and barriers that the river is physically restricted by. And then also bead size. These are all factors that we as practitioners can't change and will have to examine and work around in order to understand the conditions that we have to work with in our beads. So we should look for those static variables and keep those in mind. We also can look at patch density. So I kind of did a pared down version of this. My field and remotely coupled methodology, but I recommend taking a look at Iskin and Wohl. She has a Emily Iskin. She was a PhD student that graduated, I believe, a year before I started at CSU, and she has a really fantastic automated way to examine a lot of different variables of patchiness in floodplains. So that could be a really interesting metric to characterize heterogeneity. We also can look at NDVI and NDWI to get an idea of hydrology and connectivity, as I described earlier. And then lastly, I have some colleagues that have been doing some hydraulic modeling and also geomorphic assessments to look at current and historic conditions imposed by dams. Specifically, if you're looking for names, I don't think either of them have published research, but Connor Mertz and Kayla Schultz, they have done some really fantastic research in the Kawanichi Valley of Rocky Mountain National Park. But they did some really interesting things to show the differences in connectivity between channel and floodplain that resulted from the imposement of dams and then the subsequent breaching and or removal of these dams over time. So all of these can give us a better idea of what we're working with and what we could have in conjunction with our looking in the field for what like other indicators of activity. And lastly, for our managers, how do we manage these sites? How do we start to think about restoring them and keeping them intact and keeping them functional? So as I mentioned earlier, some aspects of functionality are inherent. We can't change them. Or they change on very long time scales. However, I widely believe that reestablishment of this floodplain channel connectivity can help us reactivate these beaver modifications. So knowing that they are persistent and knowing that they are retained even after incision occurs and after connectivity is lost, if we are able to refill up this bathtub that the floodplain essentially functions as, then we are able to re-enjoy the benefits of these features. And we've actually seen, I also, part of my research that I kind of eliminated for the sake of keeping this talk a little bit smaller, was that there are a bunch of different restored sites I looked at. There were 5 of them. And specifically, there's 2 that are going on in the South Fork Pooter. And one of them at Lazy D Ranch, they have had successes in refilling a beaver meadow due to some a varied number of structures and decisions they've made to try to establish connectivity, but they've had success in naturally rediverting water into this beaver meadow and reactivating it, which is just super awesome to see. So it is possible. And in the South Fork Pooter, they were actually able to, I'm not so sure about how they did this, but they actually had beaver return to it recently, which is, again, more fantastic news. So this is very possible. And it fills me with a sense of optimism that these features are persistent and can be reused over time and can even encourage beaver to come back themselves. But like any case, there's not a one-size-fits-all strategy. We have to be very careful to look at what we're working with, like I've emphasized, and they also depend on the desired outcomes of the project, both scientifically and what people, shareholders, stakeholders, what managers are looking to achieve. So it's very important to consider the context of your site, both scientifically and also on the other side, who are our users and who is benefiting from it and who do we need to keep in mind. But like any science, there's still a lot of things we need to know. So specifically, I kind of introduced this idea that the nature of beaver meadow degradation is pretty complex. Tried to categorize into 4 different categories, but I think there's still a lot to learn there. I think there's still a lot of research that needs to be done on specifically like the timeline of this degradation, and also just a little bit more detail into the signatures of that degradation. In kind of going along with this idea of timeline, we also need to figure out a better concept of how fast these sites can recover. I assume this is probably on a case-by-case basis, but generally giving an understanding of what it looks like to restore a site. And also, like I alluded to earlier and wanted to come back to, I am doing my PhD. Specifically, I just cannot get enough of these beads. I think they are absolutely fascinating and I love researching them. And so what I've decided to do is look at some different beads in different mountain systems, different regions of the US, different climates. Specifically, I've expanded out to Appalachia and I'm looking up in Pennsylvania and down in North Carolina. And I'm trying to see if there are differences in these beads, both geometrically, how they're distributed, whether there's beaver acting in them, factors like that to help understand similarities and differences that might influence management on a national scale. And also just hopefully trying to bring attention to these really, really important and delicate sites. So with that being said, just to kind of summarize what I've shared with you guys today, we can see that deactivation of beaver meadows can change process domain and functionality. So going back to the idea that our beaver meadows and out grasslands, while both very patchy, have differences in their have differences in their hydrology. However, Beaver-induced complexities are not necessarily lost as soon as this deactivation occurs, and they can be reaccessed. And coupled fieldwork and remote sensing can be integral in site selection and monitoring, and also for restoration. So with that being said, I had a lot of really, really awesome people and sources that helped me out. So I just want to acknowledge the USDA, GSA, Warner College for helping with funding. I had some field help by Shayla Triantafilu, Owen Richardson, Aaron Cates, and my lovely mother, Alyssa Larkin. Thank you, Mom. I also had help from Taryn Contento and the cloud, Larry Dale and Scott Barker. And also I wanted to shout out to my wonderful, wonderful advisor, Ellen Wool. She is awesome. She is every bit as great as you guys have heard, and she is a fantastic scientist. I'm very, very lucky to work under her. And I'm happy to keep providing interesting science to everyone out here. So with that being said, thank you so much for taking the time to listen to my talk today.